Imagine you've just changed the structure of the data your application stores. A new field was added. An old field was renamed. Maybe a value that used to be a string is now an object. You can't restart every server at the same moment. In any real system, you deploy gradually, a few nodes at a time. For hours, sometimes days, old code and new code run simultaneously. Old code writes records that new code must read. New code writes records that old code must read. This is the problem Chapter 4 of Designing Data-Intensive Applications is about. Not just how does data get stored, but what happens to your data when your application evolves. The book names the two directions of compatibility precisely because the distinction matters in practice. Backward compatibility means new code can read data written by old code. That's the easy direction. You wrote the new code, you know what the old code produced, you can handle it. Forward compatibility means old code can read data written by new code. That's harder. Old code has to gracefully ignore fields it doesn't understand, because those fields didn't exist when it was written. In a rolling upgrade, also called a staged rollout, both directions have to work simultaneously. If you break either one, some nodes in your cluster will start failing to read records that other nodes wrote. How do you achieve both? That depends entirely on the encoding format you use to turn your in-memory data structures into bytes, and that's what this section covers. We'll look at the human-readable formats first, JSON, XML, and CSV. Then at binary formats. And by the end, you'll see clearly why schema-based binary formats are not just a performance optimization, they're a correctness guarantee. JSON became the lingua franca of the web. Almost every API you interact with speaks JSON. Most developers reach for it without thinking. So let's actually examine what JSON does well and where it silently fails. JSON's strengths are real. It's human-readable. It's self-describing. You can look at a JSON object and understand its structure without a separate specification. It's supported in every programming language. For small-scale data exchange between services, it's often entirely adequate. But JSON has three significant weaknesses the book calls out. First, numbers. JSON makes no distinction between integers and floating-point numbers, it just has number. That sounds minor until you hit a real production incident. Twitter uses 64-bit integers for tweet IDs. When Twitter's API returned those IDs as JSON numbers, JavaScript clients silently corrupted them because JavaScript's number type is 64-bit float, which can only precisely represent integers up to 2 to the power of 53. Twitter's fix: return tweet IDs twice, once as a number, once as a string. Let that sink in. The world's largest real-time platform had to double its ID field just to work around JSON's number type. Second, binary data. JSON has no binary type. If you want to include image data, a cryptographic hash, or a file attachment in a JSON document, you have to base 64 encode it. Base 64 increases the data size by 33%. Third, schemas. JSON is optionally schemaless. You can add JSON schema to validate structure, but nothing enforces it. Two services can agree informally on a JSON format, and slowly drift apart. Extra fields added here, types changed there, with no system-level enforcement. XML and CSV have parallel problems. XML is notoriously verbose, the tags take up more space than the data in many documents. CSV has no standard type system at all, every cell is a string, and the interpretation is entirely up to the reader. For simple human-readable data exchange, these formats are fine. For high-volume, high-reliability data pipelines with evolving schemas, they start showing cracks. If JSON is so verbose, why not encode it as binary? Strip out the human-readable formatting, encode values more compactly, and you'll save bandwidth and storage. This reasoning led to binary variants of JSON, MessagePack, BSON, BJSON, UBSON, BISON, and SMILE, among others. Of these, MessagePack is probably the most widely used. Here's a concrete example the book uses. Take this JSON object, username, Martin, favorite number, 1337, interests, daydreaming, hacking, encoded as plain JSON with whitespace, that's 81 bytes. Encoded with MessagePack, it's 66 bytes. That's a savings of 15 bytes, about 18%. But pause and consider what you gave up to get those 15 bytes. You can no longer look at the raw bytes and understand what they say. You need a MessagePack library to decode it. If something goes wrong during transmission, a truncated message, a corrupted byte, diagnosing the problem is much harder than reading corrupted JSON. And the savings are modest precisely because MessagePack doesn't change the structure of the data. It still encodes field names as strings. In the example above, the string username appears in every single record you encode. If you have 1,000,000 records, you store username 1,000,000 times. The encoding is more compact per character, but the fundamental redundancy remains. This points at the real source of inefficiency, not the encoding of values, but the encoding of structure. Field names are metadata, they're not the data itself, and yet in JSON and message pack, they travel alongside every single record. Eliminating that redundancy requires something more powerful, a schema. When both the writer and the reader agree in advance on what fields exist and in what order, you no longer need to include field names in the encoded data at all. The savings that follow are not 18%. They're much larger. Here's the insight that drives the design of the most efficient binary encoding formats. If both sides agree on the structure of the data in advance, the encoded bytes don't need to carry any structural metadata at all. Think about what a JSON record actually contains. Half of it is keys, the string's username, favorite number, interests, repeated in every single record. The other half is values. In high-volume data systems, you encode the same schema millions of times per second. That's an enormous amount of redundancy. A schema says, we both know record type X has 3 fields. Field 1 is a string called username. Field 2 is an integer called favorite number. Field 3 is an array of strings called interests. Once both writer and reader have that agreement, the encoded bytes can drop the field names entirely. You just encode the values in the agreed order. That's the design principle behind Thrift, built at Facebook, and protocol buffers, built at Google. Both require you to define a schema in an interface definition language before writing any code. Both generate code from that schema for encoding and decoding. And both achieve dramatic space savings compared to message pack or JSON. The book gives the exact numbers. The 81-byte JSON record becomes 59 bytes with Thrift's binary protocol, 34 bytes with Thrift's compact protocol, and 33 bytes with protocol buffers. That's more than a 2.5x reduction from JSON, not by encoding values differently, but by eliminating field names entirely and using compact field identifiers instead. But the schema doesn't just save space. It also creates a mechanism for managing evolution. When you need to add a field, or rename one, or change a type, the schema is the place where those changes are tracked, and the encoding format is what enforces that both old and new code can handle the transition safely. That's the real value. The next section shows exactly how that works.